Welcome to the NMENA video tutorial about concentrating solar power. This lecture is about solar chemistry and solar fuels. It's in the Unit 1, Block 6. My name is Christian Sattler. I'm head of the Department for Solar Chemical Engineering at DLR's Institute of Solar Research. I'm working for more than 15 years in solar chemistry and solar fuels, and I'm promoting CSP around the world in many positions. Solar chemistry and solar fuels is a little bit away from solar power production, although it uses the same sunlight as these technologies. But we divide it into two basic principles, thermochemistry and photochemistry. The applications of these technologies are solar fuels, solar materials as the main applications, and other applications like solar chemicals. I will tell you a little bit about what is happening in this field, how the technology is used, and the perspectives of these technologies. The basics of solar chemistry is that we have two role models. Photosynthesis, like in plants, we use the photons of the sunlight for carrying out photochemical reactions. And the other one is using the sunlight, like in a burning glass, like in CSP plants, for heating up thermochemical reactions. But there is a principle in chemistry that photochemistry is forbidden when thermochemistry takes place and vice versa. So if we do something in photochemistry, it's always cold, and if we do something in thermochemistry, it's always hot. However, in some cases, there are synergies between both. For example, in the treatment of wastes, where as well photochemical effects as thermochemical effects can help us to do the job. Why do we use solar chemistry instead of solar power? We could generate electricity from solar power and then carry out a lot of these chemical reactions, for example, by electrical heaters, by electrochemistry, even by running lamps with it. But if we use the sunlight directly, we could reduce the conversion steps. So, for example, if you would like to produce hydrogen from water, you have to split the water molecule, and if you use the solar chemical way, you just need two steps: the conversion from solar radiation into heat, and then the conversion from heat into chemical energy. If you would use it via CSP, you would have four conversion steps: from solar radiation to heat, from heat to mechanical energy, from mechanical energy to electrical energy, and then from electrical energy to the chemical reaction. If we use solar photochemistry, we only have one step, the step from light directly into the chemical reaction. So this is especially efficient. However, photochemistry is not so common in chemical industry. There are only a very few processes, but there's one large process in the production chain of nylon, which is the production of the raw material caprolactam, with an annual production of more than 200,000 tons. Unfortunately, this is run by artificial light, and we are developing technologies that in the future we can run this with solar reactors. The main research fields in solar chemistry are the photochemistry, obviously, which is artificial photosynthesis to generate fuels in the same way like plants do it. Plants produce sugar out of sunlight and CO2. Chemists try to produce hydrogen or synthesis gas out of CO2 and water and sunlight. There are some chemical products like the caprolactam already mentioned, and also some fragrances that are already produced. And there is a small research group in the world that is working in this field. There's more activity in thermochemistry, obviously, because solar thermal developments are much further introduced into the power market. The main technology that most groups focus on is the reforming of carbonaceous materials to generate fuels, or to upgrade fuels with renewable energy. The fuels are then hydrogen or synthesis gas, and from synthesis gas, liquid fuels like gasoline or methanol. The next reactions are the splitting of substances with a low energy content like carbon dioxide or water to generate fuels, also hydrogen and syngas. There are also possibilities to store heat in chemical reactions and to produce and recycle materials like metals or ceramics. As this tutorial shouldn't be too long, we would like to concentrate today on solar fuels. In this slide, you see the ways how to generate solar fuels from solar energy. And all the boxes with the big blue lines around show you how the heat is introduced into the generation of fuels. And the main way is always the conversion from solar energy into heat, then over the solar thermal process into the production of hydrogen, and from there into synthetic fuels. There are no synthetic fuels without hydrogen. The hydrogen is absolutely necessary because the energy that we would use in the fuel in the end is the bond between the carbon and the hydrogen molecule. There are also some photochemical ways, which you see on the right side. And of course, you could add, as already mentioned, some additional materials like fossil resources as natural gas or coal or biomass into this process to generate the fuel that you need. As in CSP, we use the same concentrating reactors like parabolic troughs, solar towers or dishes. However, the most important reactions take place in a temperature range between 600 and 1500 degrees C, so solar towers are the installations that are best suited to run the technologies. Solar dishes are too small. Chemical engineering, you like to have bigger reactors with very constant conditions inside, and the temperatures that you can achieve in parabolic troughs are not high enough to run the chemical reactions desired. But there are limits to all these installations. Of course, we can go to very high temperatures with solar thermal installations. We must have in mind that the higher the temperature is, the higher our re-radiation losses are. So the chemical reactions that take place at very high temperatures are efficient, but the installation becomes inefficient. Here is an example from solar power tower, and you see that the efficiency goes below 20% when you are in temperature range of 1300 degrees C. So taking into account material problems, taking into account the re-radiation losses, it is crucial not only have the right concentrator, but also to have the right reactor, to adapt and design the reactor to the needs that you have for running your process. There are, of course, a lot of solar towers, especially for research, already established in the world. Some are even for commercial power production, like the PS10 and PS20 in Spain. How would we use such solar towers then for solar chemical installations? We need the heat, we need the chemical reactor, and we produce the heat by our solar tower. And then we add in our chemical reactor our resources like natural gas, water or carbon dioxide, and produce in the reactor our fuels like hydrogen or syngas. And from there, we can either use this mixture directly for industry or for transportation, or we can convert it into fuels and then use the fuel in, for example, a fuel cell for energy production, but also to generate other materials that can be done from the solar fuel. As I have already introduced, there are technologies that can be done on the short term, and the most prominent are the solar reforming reactions. The benefit of this is that you store energy and reduce therefore CO2 in your produced products like the solar syngas or solar coal gasification. The reaction is pretty simple. You have water and methane to produce hydrogen and carbon monoxide, or carbon dioxide and methane to produce hydrogen and carbon monoxide as well. Only the ratio is different. It is very common to use mixtures of CO2 and hydrogen to produce syngas, and it is very interesting that you can use natural gas wells with a high CO2 content, which are not suitable for natural gas production, to produce this solar syngas, because the added value of the sunlight makes out of this mixture a valuable syngas that can be used for fuel production. Out of these mixtures, you can then produce, for example, methanol as a liquid fuel, as already shown in a number of projects. The reactors are crucial, as already mentioned, and there are in principle 3 types of reactors developed for the technology. The first and most simple technology is to use a classical heat exchanger reformer as used in chemical industry today, and couple it with, for example, an air receiver that produces the hot fluid to heat up the reformer. This was shown in the Asterix project already in the early 1990s. The benefit is that you could run this installation with a heat storage for 24 hours a day. The problem is that the efficiency of this reactor is not as high as of the other 2 technologies that I would like to introduce now. These are the indirect or tube reactor. There, the reaction takes place in directly irradiated tubes filled with a catalyst. The efficiency is higher in this technology, but there are thermal stresses on the tube wall, and as the sunlight only comes from one side, there is also a thermal stress between the front side of the wall and the back side of the wall. So the efficiency is higher as with the allothermal reformer, but it is more difficult to run, and it can only run if the sun is shining. So a continuous operation is not possible. These developments are, for example, done by the Australian CSIRO, but also by colleagues from Japan, and also in Germany and Israel work is done on this. Australia plans to set up a larger plant of this technology to demonstrate it. It is called SolarGas, and it is a lighthouse project of CSIRO. The most advanced technology is the integrated or direct volumetric reformer. Here we use a volumetric absorber coated with a catalyst and used in a pressurized vessel. With this technology we can achieve the highest efficiency, but also there we have some drawbacks. It can also be run only in direct solar irradiation, and we need a glass window to operate it. However, there seem to be niches for all these three technologies to operate them, especially combined with natural gas wells. Here I show you some pictures of the already built installations. This is the Asterix plant built in the 1990s. It was operated on the large Cesar 1 tower in Algeria on the Plataforma Solar. This is a sketch of the CSIRO tube reformer, which will be set up on the small solar tower of CSIRO in Newcastle in New South Wales, Australia. And this is the Solref plant operated on the tower of the Weizmann Institute of Science in Rehovot in Israel. And as you can see here, we could achieve methane conversion of 78%, which is the theoretical balance. And we could operate it at 15 bars. The largest installation for reforming, however, was on a different process. In the SYNPET project, residues from oil refining were used to produce a syngas, and the reformer used there, also on the Plataforma Solar, but on the smaller tower, was a 500 kilowatt thermal reformer, and to my knowledge, it is the largest solar thermochemical plant already installed. Where can we set up such installations? So here you see as an example where in Algeria we find places that are suitable to run in. We say there are about 3 conditions that must be fulfilled. There must be, of course, enough solar radiation. This is shown by the yellow and orange lines. The brighter they are, the better the place is. And then there must be the near to, as well, natural gas wells as to a pipeline system to bring the reformate to the users. We say that a distance of 50 kilometers is possible, and then you should have a connection as well to the gas well as well to the pipeline. And you see here that there are some white spots in our corridors, and these are places that, for example, are too steep or where buildings are or cities. So anyway, we have a lot of space available, for example, in Northern Africa to set up such plants and to enhance the energy content of the available natural gas. This would reduce the CO2 emissions drastically, as shown between 25 and 50%. Coming now to the long-term processes, in this we would like to avoid the carbon from the beginning. So we take as a resource water, which we split into hydrogen and oxygen. Here you see as a comparison why it is so interesting to use solar thermochemistry for these processes. Our colleagues from the SANDIA National Lab in the US have compared the production of solar thermal power and the electrolysis run by it with a conventional electrolyzer with these solar thermochemical processes. And as you can see, the annual efficiency for the solar thermal power plus electrolysis is about 14%, whereas the high temperature processes range between 20 and 25%. One is a high-temperature steam electrolysis. There, part of the electricity is supplied by the heat, so you could reduce the amount of electricity. And then, even more efficient are so-called thermochemical cycles, where you don't need any further electricity to run it, but you use heat as the main energy input. Some of them can, of course, be run in hybrid version as the hybrid sulfur process or the hybrid copper chlorine process. There, one of the steps is an electrochemical step. So they are very much comparable to the high temperature steam electrolysis. However, the process used are more efficient than the water electrolysis. The most efficient process are so-called two-step thermochemical processes where only metal oxides or metal are used to split the waters. Here, efficiencies up to 25% could be achieved. These are the most prominent thermochemical cycles already worked on. They are in 4 classes. The first one is the sulfur class, already known for several decades. They were firstly developed for nuclear power. Therefore, the common names for them are Westinghouse and General Atomic Cycles. They have the benefit to work at rather low temperatures for 900 degrees C, but they are very corrosive. However, we see good chances that they will be interesting processes to scale them up to a certain size. In volatile metal oxide cycles, zinc or cadmium are used to do this. Here a problem is to separate the metal from the oxygen so that the reoxidation doesn't take place. More interesting seem to be non-volatile metal oxides like iron oxide, cerium oxide, or so-called mixed iron oxides or ferrites. And I will tell you a little bit more about this later. And then there are low-temperature cycles like the hybrid copper-chlorine cycle, also especially designed for nuclear power, where you have more steps, which lowers the efficiency a little bit, and you have very complicated intermediates to be treated. In principle, we believe that the sulfur and the non-volatile metal oxide cycles have the best chances to get into application. As I can explain all these technologies, I would like to tell you a little bit about the ferrites. The process works rather simple. You have a coated ceramic structure where your redox material is fixed. You heat it up to 800 to 1200 degrees C, and the material is reduced. It is able to absorb oxygen. Then you put steam on it, or water as steam, and the material is oxidized, and so the oxygen sticks in this material and only hydrogen is set free. So you have a very clean hydrogen stream. Then you have to recycle your material, that is only by heating it up to 1200 degrees C. And while you do this, oxygen is released from the material and you have the reduced material again, which you then can use for water splitting again. The net reaction is only water splitting into hydrogen and oxygen. This was developed by several groups into several different reactor types. I will present you one here, the so-called hydrosol type. There you have two chambers. Here you can see it already scaled up into the 100 kilowatt range and tested on the smaller tower of the Plataforma Solar de Algeria. We have two chambers and you can switch between both of them. So on the first run you have on the left side the water splitting, and on the right side the reduction, and then you just swip it, you reduce the left side, you split the water on the right side, and so on. And so you can produce quasi-continuously hydrogen and oxygen out of this machine. The next step will be to scale this up in a, let's say, demonstration scale, so that you get into close to industrial size in the megawatt range. And for that, you need to fulfill some things. Such plants needs a very advanced control system. Chemical reaction needs very even conditions in the reactor. So the control system needs to control the heliostat field, it needs to control the temperature in your reactor, and it needs to control how much the chemical product is produced, so how much hydrogen you have. And all these different models must be put into the control unit of your plant, and this must control how you operate such an installation. And if you can imagine, a heliostat field is huge, the reactors are huge, the temperatures are very high, you need very even temperatures. It is really a challenge to design such control units. Here, as an example, I show you how the heat flows are in one of these reaction chambers, and this is only one part of the model that we use to control our reactors. The model is already available, and we can control such units very efficiently on the tower in Algeria. Here, as an example, you see the black line is the measured temperature of one of the modules, and the red line is the simulated temperature. And you see here the regeneration step at 1200 degrees C, and here the production step at about 850 degrees C. And we are very comfortable with this model and could show in a lot of test runs that it works in a very good way, and we are certain to be able to scale this up in the megawatt range. So what is the conclusion and outlook of this solar chemistry and these solar fuels? What we would like to have is a future solar thermal plant that not only produces power as a standard CSP plant, but uses the heat for a different or many other applications, like fuel production, like water desalination, so that you can do anything with the already very expensive heat most efficiently. I come now to the end of this tutorial. Thank you very much for your attention. And don't forget, objects in mirrors are closer than they appear.